talking about the concepts. So first we will try to understand what is the system, and that is system related to energy here, and in particular solar energy or any renewable energy sources. So I would say that we call this a system. System sometimes can be called as device, and sometimes we call this in engineering prime movers. So basically, the system here, uh, uh, we can say that any device which convert one form of energy which is available to us into useful form of energy. So basically, I consider here that the meaning of the system, and of course is a energy and solar energy. So our focus will be that how we can convert the available form of energy into useful form energy through by designing a system. Which system? Because the designing I'm talking about. So I can say that if you are a good designer, so at least the three things you should keep in your mind. One is the system, of course, should be efficient, and it should be reliable, and finally it should be cost effective. So I think if you keep these three things in mind, and then you can design the system so that the available form of energy can be converted to useful form energy. So basically, I'll start with this solar energy. Now, that's one more thing I always used to say that when we talk about the renewable energy sources, that because engineer's task is to design the system. So I used to tell that sometimes what we don't just focus the other aspect, which is very much related to design the system, which I told you that the cost effective, reliable, and efficient. So we should understand the form, that means the energy input form of the energy, and we should understand its nature also, and basically in what form it is available. Then we will start, we can think about the designing of the system. And the one more thing is there, especially in particularly I'm talking about in solar energy. That means when you will start designing the system, you should start with how much solar energy is available to you, because it is not sure. That means if you talk about the conventional source of energy, or even up to certain extent, I can say the hydro power. So we can show that up to certain for a period of time, say 2 days, 3 days, or 3 months, 2 months, we can say that at least for one day, we are sure about that this much energy available to us. But you cannot say about the solar energy. So that means I think it's a very much time dependent. So before you start designing the system, you should discuss or should be clear about the nature of the solar energy, how it is reaching to you, so that you can take the as the input to your system. Based on that, you will design. And one more thing is also there related to solar energy, that in the very beginning, you have to decide that in what form you want energy. I'm just talking about this hydro. So hydro is always converted into electricity first. Then after, suppose you need the thermal energy, then you can convert this after this after generating electricity, and then electricity can be converted to thermal energy. But this facility is with solar energy directly. That means if you need the thermal energy, your requirement is of thermal energy, so there is no need to generate electricity first and then convert it into electricity. Directly you can tap the solar energy and convert it into thermal energy. So that is the beauty with the solar energy. And it is always there. That means in the beginning itself you have to decide that what form of energy you need, in what form your energy requirement is. And if you know electricity, so again it is directly converted into electricity. That is also beauty, and sometimes it looks like a magic that the solar radiation are reaching to our surface, and then you are collecting that, you are intercepting that on a surface area, on a material, and one material is getting heated up and another is generating electricity. So that means these things you should keep in your mind when you deal with the solar energy. Of course, I'm talking about the concepts and the basics. So in that case, let us start with that. Let us understand that how the solar energy reaching to Earth surface. So this is the things I think it's, everybody knows, your faculty, you are already know about the solar energy. We can say this, the sun is the prime source, because all the renewable energy are derived from the sun energy, that means solar energy also. So our concern is basically not that energy which is converted in other form like biomass, I can say, that is also derived from the sun. This hydro cycle, that's the hydropower, is also from the sun energy also. Wind also are derived from the this solar energy, and some energy which cannot be available to us. So our concern is in this part, that this part, that about 47% of total energy which is coming from the sun towards earth can be tapped. So that our concern is this. So this is one thing we can say, that then again we have to discuss in what form and how this is reaching to our surface. So that even then, sometimes I tell you that you should not start designing the system without knowing that whether the potential is available or not there. So as far as the solar energy in India, we are lucky that the maximum solar radiation, we are falling in this belt where the solar radiations are having of the we can say the maximum, because the maximum is 300 on an average over a 24 hours is watt per meter square. But we are touching that. That's about 250, between 200 and 250 watt per meter square if you take the average solar radiation over 24 hours. Yes. So that means here we can say that this country would represent about 250. So that means this is crossing the our country. So that means we are lucky enough, that means we have a lot of potential of solar energy. This is also that you also know that about this the sun has a lot of energy, so that means worth this energy demand can be fulfilled, and then it's more than 10,000 times more than which we need in the world. And it is also that there are tedious tasks in order to estimate, and that is the some drawbacks with the solar energy. That means we cannot be sure that at this input of the solar energy for the system. So we can estimate. There are so many techniques, very advanced techniques are there in order to estimate the solar radiations or solar energy. But we have estimated that in India there's about 2,100 kilowatt hour per meter square per year. That is the range of the energy we received from the sun. So based on that, it is, of course, we can say it depends on the time, it depends upon the season, it depends upon the weather condition, and it will depend upon this location also. But on an average, we can take this figure. Now that, as I'm telling you, that this we should understand that how this 47% energy, and out of that, how much we can use that. So let us think about that. That the sun, continuously, we can say that the solar radiations are coming from sun, and that how this sunshine, that means I can say that the energy in the form of the solar radiations, that is the working parameter we call that. So because in order to estimate any renewable energy or any kind of energy, so you need to measure a parameter which I call is a working parameter. So here this working parameter is solar radiation. And the beauty with the solar radiation, again I'm telling you that there's no need to apply the power equation in order to estimate the solar energy. It is the parameter, this working parameter has unit, almost the power, that is power per meter square. That solar radiations are measured by watt per meter square. It can be kilowatt per meter square, joule per second per meter square, because we need power in watt. So that means by considering the area over which you can taking the solar radiations, so we can directly get the power, this potential, that means the watt. So that's there's no need to have the suppose in case of hydro, you have to measure discharge, you have to measure head, and then you have to apply the power equation, that is 9.81 into Q into H, and then you get the power. But here, whatever you measure with the instrument, that will give the directly power. So that how this solar radiation reaching to Earth's surface. So we are here. We can be located at any place, because you know that our this Earth surface is not flat with respect to the sun. So it is like this only. So anytime. So what is that? The some solar radiations coming, they are passing through the space. This I call this space, and this is I call this atmosphere, because this and this is the Earth surface. So around the Earth surface there is the atmosphere, and beyond that is space. So when this sunshine or the solar radiation travel through in space, so there's not much, we can say that this intensity remains constant almost. But when it enters in the atmosphere, then problems that means arise. That what are the problems? That means some solar radiations which can be reflected in the atmosphere and reflected back to the atmosphere within the atmosphere, I can say, but it is not reaching to Earth's surface. So that means it is not available to me, because my system will be placed on the Earth's surface here. So that means the solar radiation which can be reflected back to atmosphere, which may not be, sometimes it may be available, but in most of the cases not available. Then some solar radiations, it enters in atmosphere, but it is reflected back to space, that is also not available to me. Then another form is, I can say that if the solar radiation find the conditions in the atmosphere almost in the space, that means no disturbing element comes. Disturbing elements, I can say, it's a dust particle, water vapors, or anything or any gas is available, clouds are there in the atmosphere, that may disturb this incoming solar radiation. But sometimes we find that some solar radiation reaching to Earth's surface without getting disturbed. So that solar radiation will we call this a beam radiation or direct solar radiation. So this is available to me, that part is available to me. And I can say that when the atmosphere is clear and the sky is clear, and you can say this is a good weather, means the atmosphere is clean, like in hilly areas. So that time I can say that most of the solar radiation reaching to me in the form of the beam solar radiation. They are not changing their direction or intensity directly reaching to me. And some solar radiation, a part of the solar radiation, when they enters in the atmosphere, but they are diffused. They are diffused means the solar radiation, because its original direction or its direction was this when it enters in the atmosphere, but after reflection, deflection, or reflection by the particles, can be water vapors, can be dust particle present in the atmosphere, so that it changes direction, and it may lose its intensity also. So that solar radiation will reach to me, but indirectly. So that solar radiation is known as the diffuse solar radiation. So these two parts are available to me. And some already, because this weather conditions, you feel that sometimes hot, so and during cloudy, because most of the energy is most of the solar energy get absorbed in the atmosphere. So that is also not available to me to convert into useful form of energy. So I think this is what I can conclude up to this point. I can conclude that the solar energy reaching to me, reaching to our surface in two components, having two components of solar radiation, that is beam radiation and the diffuse radiation. So that is the things. So in that case, I have to work out, I have to design my system by considering that mainly these component of solar radiation. Then sometimes we may be interested to know that what could be the maximum possible solar energy or solar radiations we may get uh, on the Earth's surface. So there is a, I think this I can say, there is a term which is frequently used in analysis for modeling or for the simulation or to design the system. That term is known as the solar constant. That's a very important term. You have to remember this, the solar constant. So this solar constant is nothing but, suppose I can say, definition is already there, but I think to make you understand that, that means if this is the sun here, this is the sun, and around this is earth surface, and around this there is an atmosphere. So how we can get this maximum possible, that if the solar radiations falling over a receiving surface where I will, and that receiving surface is of unit area, and it is just kept perpendicular to the incoming solar radiation, because that is at that condition only the intensity of solar radiation will be maximum, when the solar radiation will fall on the receiving surface perpendicularly. Where we have to cap this receiving surface just outside the atmosphere, just outside the atmosphere. That means that value will be the maximum possible value of solar radiations which will enter. Sometimes we may get about that, or it cannot be more than that. So that is the that is known as the solar constant. It can be represented by sometimes SC, that is the, or HSC, that means H is for solar radiation, and SC means the solar constant. So you can read that this is self-explanatory. That means it is the maximum possible value of solar radiations intercepted over a unit area when that receiving surface is kept just outside the atmosphere, and the solar radiations falling on that receiving surface at perpendicular at 90 degree. So that is that value, and this is of course I'm using this 1353 watt per meter square, but there is some variation in it may be 36, it will be around here, so that in some reference you may get slightly, but it cannot be 1500, or it cannot be 1200, or it cannot be, so around this. So that means this is known as the solar constant. So I just, why I'm discussing this, that whenever that is because the when modeling and simulation, or there's some analytical work you have to do without considering the practical setup or the actual setup. So in that case, you have to assume the range of the solar radiation or range of the parameters. So I tell you that in no case you should assume that solar radiation maximum in solar energy area I'm talking about, beyond this solar constant. So it should be under that only. Of course, sometimes that is, I don't discuss that, otherwise it will confuse you. But in most of the cases, or mostly, the maximum solar radiation should be under this solar constant. That's why that's the important term. Okay, so that this already I have told you that somebody can give me your response whether is okay, or you want to in a different manner, so that I can change my style of talking here. Hello, participants. Any
So I'm just providing everyone the right to unmute themselves. So
yeah,
till now, like they
one.
couldn't unmute.
Okay, 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 okay. So that they
So
cannot.
now they can speak. Yeah,
Okay.
now
Sir,
they can speak.
Sir, it
Yes,
is
sir,
excellent
your base is
and
good. Whatever
excellent.
the delivery you are taking, it's good.
Uh,
Sir, it is good. It is good.
okay, okay, okay. So
Sir, excellent,
hello.
excellent.
Okay, so thank you, thanks. So
Sir,
It's
that
okay. It's okay, sir.
okay, that will encourage me to,
It's okay,
to
sir.
talk like. Okay, thank you. So let me continue. So this is we can say that now this beam radiation and solar radiation, and there's another terms we use. It's a, I think, concept I'm talking about. So there are so many terminology used for different. So you can ask me that, I can clarify, but I'm using that the very basic terms which are used in this solar energy. So that means the as I told you, that beam radiation, beam solar radiation I'm talking about, sometimes it is known as the direct solar radiation, normal direct. So these are the terms, but basically these are the things. So here there mainly beam radiation and diffuse radiation we are using, and I just put here also this, I just use H for radiation and B for beam radiation, and this is for diffuse radiation. And then I may have this, some of these that will be known as the total solar radiation. Sometimes I call this terrestrial solar radiation also, because it is entering to the means in the atmosphere, and it can be tapped 100% in this ideal condition I'm talking about. And the solar radiation which is beyond atmosphere, that is known as sometimes the extraterrestrial solar radiation. So that I'm interested in terrestrial solar radiation. So so this is that HB plus HD. So this is the things I'm interested in. Now that the problem with this measurement of is that it is every second it may vary. So that it is highly time dependent. The incoming solar radiation is highly time dependent. So it is and you know that, because as an engineer you know that to design a system, that system can be designed for a particular rating, for a particular specification. For suppose I want 2 kilowatt system, 3 kilowatt system. So that means that 3 kilowatt output against some input only, na? So that input I have to take one value. So that means in solar energy, what value I should take that to design my system so that it will deliver the desired power. So that is very important. So again here, because the time constraints is there, so I'll just discuss the basic things how you will tackle this input for the system in the solar energy. That means you have to estimate, and you have to take the in mathematics we can the average value, and this average is very vague term sometimes. So I use that term, that is a good average. That means the average should be there, but it should be good average. So that means that your three things, efficiency, reliability, and cost should not be affected. So that is the concern here. So that means we know, of course, we will use this location term also will use while estimating the solar radiation. Time of the year also will use, time of the day also, and of course this I'll discuss in the following slides. And of course this climatic conditions which are not in our hand. So there are so many these models nowadays, they are using considering the different conditions, climatic conditions, so that you can have the good average value in order to design the system. So this is the solar energy is very simple energy, and you can say even the instrument is very simple instrument. The simple instrument, there is this glass bulb. In this there is a sensor. The sensor may be thermal energy principle, or it may be PV nowadays. So what is there? The solar radiation falling on this, and they are absorbed here, and this energy is calibrated in the form of directly we will get the watt per meter square. That is the simple things, that whatever solar radiations will fall over here, that will be directly measured with this instrument. This is known as there are so many other uh, terms used for solarimeter, but I'm using this as solarimeter. Simple. You can if somebody say which instrument is used to measure the solar radiations, you can say okay, solarimeter. It's nobody will say that this is wrong. Uh, so that means watt per meter square is the solar radiation. That is the working parameter. Then I tell you that when I discuss that there are two components of the solar radiation, that is beam radiation and diffuse radiation. So we can measure these combined. Combined means, let me tell you that here, suppose this is the sensor and it is capped on Earth surface, and solar radiations coming from sun. Whatever solar radiation, under these conditions, even I'm not protecting the beam radiation or diffuse radiation. The beam radiation is also falling here, that is there directly, or that may be indirectly, but those are falling on this receiving surface or the sensor. So that means the total solar radiations are measured under these conditions. So I cannot say that the reading shown by this the solarimeter will be H only, but I don't know how much beam radiations are there out of this and how much diffuse solar radiation. So then the question is there necessary to do that exercise? Because if some energy is coming to my surface, my receiving surface, my system, I will consider the total solar radiation. But I tell you here, that means that's why it's related to the basics of the solar energy system. So now there are some systems which work on solar energy may not take this diffuse solar radiation. They will take only beam radiation only. Beam radiation, I can say, that means which is directly coming. The solar radiation about exactly its nature, actually its direction, that is known beam radiation. Suppose the sun is here and you are on the surface here. So at this location, at that time, you should know all about of this solar radiation. That I should know, because you know that all the details, all the relationship between the earth position, your position on the earth and with respect to sun. There's another engineering, you know that, and based on that you can determine that what will be the direction of the beam radiations reaching to our surface, because this is the definite, because I'm sure that it is not changing its direction on the way. But for diffuse radiation, suppose this diffuse radiation is coming in this direction, up to this you can know, but to you it will be coming in this, and I don't know these conditions. So I don't know about this, in which direction it will come at that time or at that particular location. So that means nothing, I don't know anything about this, only I know that what is the amount of that. So in these conditions, the total solar radiation I'll be able to do, but I don't know that how much HB and how much HD. And why we need to separate it out? Because some systems are designed based on this. So that means if you measure this and you use this data to design, to size your system, like the focusing type solar collector I'm talking about. In that case, only beam radiations are used. So that means this, if you know about this, then only you can design this. And diffuse radiation, I don't know where it will go, so I don't consider this. So under that conditions, so let me tell you here, that otherwise I'll go fast. That means suppose it is this total solar radiation is say 700 watt per meter square. So that means based on this data, if I want to design this focusing type solar collector, I should not design. So because this 700 watt per meter square, I cannot take the input to the system. What should I know? I should know that how much is solar. This suppose 400 is direct and remaining 300 is beam. diffuse, and this is beam. So I have to design based on this. So then only you can design. So that is necessity that you should bifurcate. You should measure these solar radiation separately. Now what is the technique? So there's I'll not discuss here nowadays. If you have this total solar radiation, which is very easy to measure, and then there's so many models. There's the mathematical models or the theoretical correlations have been developed, which are available in the literature, where you can determine the diffuse solar radiation, and then finally you have the total solar radiation. You can minus the diffuse radiation, beam radiation can be separated. But during measurement, I am telling you, during measurement, this in the weather monitoring stations, they are not using the mathematical expressions or the theoretical correlations. They simultaneously using beam radiation, diffuse radiation. What is that? That the two solarimeter for the same range, same accuracy, everything is same, and they install that at one locations. So what they do, they put one solarimeter, this sensor, under a shadow ring. We call this the shadow ring. That is the one attachment extra they put here. So in that case, what is this shadow ring? That means always, every time during sunshine in the day, this bulb will be under shadow. Under shadow. It should not be like that you put this under in a room. No. That shadow means this shadow of this rim should be fall on this, and this shadow ring tracking always with respect to the position between this. So what is there? That means if you are protecting, that means what is the purpose to have the shadow ring over here? This shadow ring I'm talking about. Beam sometimes, or shadow ring I call this. So what is the purpose to have that? That means every time you are protecting the beam radiation to fall over this bulb. So that means HB are protected by this. Still it is showing some reading. So what that reading will be? That will be diffuse solar radiation, because the HB at that particular location at that particular time, the beam radiations are not falling on this sensor, and the remaining diffuse radiations will be falling indirectly on this, and it will be measured as HD. It's okay. Now if another bulb, that means other sensor, is exposed, totally exposed under sunshine, which will take all the solar radiation, that means total solar radiation. So now you have two reading, that total solar radiation and diffuse solar radiation. So that beam radiation will be H minus HD. So that is the way. So that means every time, every location, you can take this reading, beam and diffuse radiation separately, and then some of this, of course, this reading this is there. So this is the things. Then next, I don't know I will be able to complete that, but anyway. So this is the thing. So finally, I tell you that in what way we arrange this solar radiation. So that means most of the cases we arrange. I tell you nowadays that in what form you want the solar data, it will be available directly from the website, from some site, from some book, already there. But this topic is on concept. So that means I'm talking about the basics thing, that how they do that exercise, which is, so the problem nowadays, we find that the research scholars, at least I'm talking about the MTech level, or this PhD level. So the PhD scholars, they start doing the work. They started working in the particular system, about the system, to develop that without discussing, without understanding the basic things. So that means because then the problems I think we are facing there. So that means it's good. That means the students or the teacher or they should at least few months or few days they should ask the students that they should understand the basics related to the system or related to the area. So that's why I'm talking about. So nowadays, immediately if I ask the student, okay, get the solar radiation in this form, he will bring that thing in within 5-10 minutes, because but he should understand how they have arranged in that. So that means the basic or the basic form to arrange the data, we call this a monthly average, hourly and daily solar radiations at a particular locations. I think that is a monthly average I'm talking about. So I'm just trying to explain here. I have put the total solar radiation, not in the three, because actual thing is like this HD and HB like this. But it is total solar radiation. That means on a horizontal plane. That is again things is that in most of the cases you will get the data, because I'm talking about suppose this is Earth surface. So, and the sun position is over here. So that means when I put my system, I call this if I put the system my horizontally at this location, if I am here, so that means sunshine will be falling over here. But at that time only somebody will be over here, and he think that his system is on horizontal plane will be like this. But with respect to sun or sun radiation, position will be like this. So that means that is the problem here. So that means data are available on these are measured on a horizontal surface. So this is the things, the monthly average. How they do that? Let me tell you that they measure. Suppose January 1st, they measure the solar radiations starting from the sunrise. That is 6 o'clock. Suppose. So that means over 6 to 7, over 1 hour, they measure 3, 4, 5, that depending on the facility, and they take the average, assuming that over 1 hour there will not be too much variation in solar radiation. That is the assumptions there. So they have taken the average hour over a hour, then next hour, then next hour, then next hour. So that means if the 10 hours or the sun signs are there, so they will have the 10 values from sunrise to sunset. Similarly, they will follow the same procedure for January 2nd, 3rd, 4th, and for the entire month of January. So now that means again there will be so many data. So then we have to take the average. That the average means good average. So in that case, what we have to do, what they are doing, that they think that on January 1st at 7 o'clock, whatever solar I'm talking about the under normal conditions, whatever solar radiations value was on January 1st, it will be, or it is on January 2nd, will be same on the same time. So that way they have again average, that for entire value for the values taken for all the 31 days in the month of January, and hourly 10 hours or whatever sun hours will be there. So they take they consider the average of each hours. That means from January 1st to 31st at 8 o'clock, what are the values they have measured? They taken the average and put one value. So that means that's why here these are the times, these are the hours in a day. I think if you can see that, and then this is the average. That means at 6 o'clock, what was the solar radiation on January 1st, January 2nd, January 3rd, and January 31st? That is the average. So that means for entire month, only one value is given. Okay, so that means if you want to take the solar radiation at a particular location, of course, this location is represented by latitude. So this is the things they measure. So that means if you want to take, that means for the entire month at a particular during at a particular hour, particular time at that location, only one value will represent. That is the thing. So that way they arrange this table. That is one thing. If somebody wants to discuss, because otherwise what will happen, I'll keep on discussing this and then we'll miss other things. So I just ask the participants, is it clear or not? If somebody can give the response. No. Okay. 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 So the our basic objective is to deal with that data. Is as I told you that means suppose you have the data HB and HD and all the total solar radiation, and these solar radiations are measured on horizontal plane. That is there. That means horizontal plane, because I have to use these at different angle, different tilt angles of my receiving surface or my system. So that is the problem. Now there's the exercise. I have to translate. I have to translate to convert, or I have to convert this data on the tilt surface or the tilt angle. So that is the things why that in a layman language, the concept I can tell you. Suppose I have this is the earth surface and here the sun. So I can say that I'm asking that what the purpose to have the tilt surface. Why we don't? Of course, you can install the solar system horizontally on Earth surface, but you may lose some energy, incoming solar energy. So in order to use that the incoming solar energy to the maximum extent, we need to tilt the surface. So I think why we need to surface is a simple way you can understand. Suppose I'm here at a particular time, I'm here and sun position is over there with respect to the this earth surface. So that means to me the solar radiation will fall at 90 degree. That means I may get the advantage of this position, and at that time only, suppose somebody is here and he kept his receiving surface horizontally like this. So that means the sun sign will be that he may lose. That means the intensity of solar radiation will not be as good as over here. So what we can do, sun cannot come over here and give the solar radiation like this. So the option is, that means you can tilt the receiving surface just to have the tilt angle, so that the solar radiation to you also, to your receiving surface also fall the 90 degree. So that means you can enhance the incoming solar radiation, you can tap more solar radiation, you will not lose the incoming solar. So that is the thing. So that means for that we need to tilt the surface. And I tell you here, because the time constraints, otherwise I discuss all the things, but I can say this, it is optimized, this angle is near to this latitude of the this location, or sometimes we can say it is plus minus 10 to 15 degree to the latitude, this tilt angle. This is the mostly we do this. So here I just take the example that if the tilt this latitude of Roorkee is 30 degree, around about 30 degree. So that means the here systems at Roorkee, most of the systems are tilted for fixed tilt angle. I'm talking about around 40 degree, 40 to 5 degree, 40 degree centigrade. Sorry, 40 degree angle. So that means this is a thumb rule based on the optimization I'm talking about. Otherwise, if you want to tap the entire incoming solar radiation, so that means this angle has to be changing every hours, every hours, so that the solar radiation should fall on your receiving surface perpendicularly. So that is the basic objective. One more thing is over here. That means if I keep this my receiving surface horizontal to the surface, so that means only beam radiations and diffuse radiation I consider. Beam radiation and diffuse radiation I consider. But when I tilt this receiving surface, so that means beam radiation, diffuse radiation falling, that is there. But what happens if this neighboring body has the tendency of reflectivity? That means the surface is of reflectivity nature. So what will happen? Because I have not protected this neighboring body from the sunshine, it will be the same amount of the same solar radiation, same intensity of solar radiation will be falling on this neighboring body. So that means if there is a reflectivity nature of this, some solar radiation may get reflected, and that will fall on this solar radiation receiving surface. So that means in that case I should consider this also when you tilt the receiving surface. Of course, if you put this receiving surface horizontally, so that reflection will go away, but it will not fall. But when you tilt this, so the receiving surface, this this reflected solar radiation will be can be received by the receiving surface. That also should be considered in the input as the input of the solar system. So what is this HR, this reflected solar radiation? This is nothing but it is HB, HD will falling on this receiving surface, and depending upon this, the reflectivity, this rho G, I'm calling this the reflectivity of the ground, G for ground. So whatever reflectivity we have, suppose it has the 100% reflectivity, so that means that the solar radiation will be doubled on this receiving surface. But that we can say the 100%. We can say that only in the mirror, this mirror we can consider is nearly 100%, but other things is maybe 20-30%, depending upon the ground conditions, ground nature. So here then again, I will not discuss details of this, but I can tell you that how you can convert this beam radiation, diffuse radiation on tilted surface. So as I already discussed that here, that means the solar radiation will depend upon the location, that is latitude. I just say that is the latitude. Latitude is represented by phi, and it is also in degree. And time of the year, that it is represented here by hour angle. I call this hour angle. Hour angle, that is omega. And the time of, sorry, this time of the day is the day of the year. Sorry, this is the day of the year. Which day you want to convert the solar radiation? Say on January 1st, number of days will be 1, for January 2nd 2, and on February 1st it will be 31 plus 1, 32, like this only. Time of the hour, I talk of the hour angle. This is one term we call this hour angle, that is represented by omega, and tilt angle is S. So these are the terms we have to consider, and I tell you here, when we the problem is that this tilt factor, because what I am interested, I am interested in HT. HT means solar radiation on tilted surface, and it is represented. It can be represented by introducing a parameter or a factor which is known as the tilt factor. This is R. R is nothing but HT by H. H I know, because the total solar radiation. And this, if I know this, then I can get the HT. But the problem is that this R is not common for all kind of solar radiation. It will be different. It will have the different value of beam radiation, diffuse radiation different, and this reflected solar radiation will different. So that means what I have to do, I have to consider the HB separately, HD separately, HR separately, and corresponding tilt factor. This R, I call this a tilt factor R. So that means this R will be RB, RD, and RR. So RB, I know that it can be, I know it will be definite, because the beam radiation, I know the everything about this beam radiation. So that means I know this, what are the factor just influencing this tilt factor is the day of the year, at which day you want to. So that means there is a terms, I'm not going to define here. So that is declination, which will be used. So that this declination term will be determined by knowing the day of the year, which day you want to do that, this declination. So this angle can be determined by knowing the name, day of the year, and then this RB is, it is derived term. It's derived term, but there's no time to derive here. But you can remember that RB will be the sine phi. Phi is the latitude, S is the tilt angle, D is the declination, and omega is the hour angle. I can say that this omega value, this is also determined value. This omega at noon, is 0 degree, and at 11 a.m. it is 15 plus 15, at 10 plus 30, like this. At 1 p.m. its value will be minus 15. 2 p.m. sorry 2 p.m. it will be minus 15, minus 30, like this only. So that means you can take this value, you can determine the RB, And RD will depend on the, because I don't know anything about this time of the year or the things. It depends upon the conditions of the weather conditions, and we can estimate this by taking of the tilt angle only. So that means 1 plus cos s by 2. Similarly, for tilt factor, this cannot be put here because we have already put in this expression here. So it is RR is equal to 1 minus cos s by this. So you can verify that if S is 0, so cos 0 is 1 minus 0. This means RR. That means no reflected solar radiation will be falling on the horizontal surface. So finally, this is the term which we use. We should take this in terms of as input to the system. That is the final. I think you have to arrive this term to take the input to the system. So far we have discussed that. So I have to be in a hurry because time constraints is there. So let us talk about the things here. So then, as I told you, this input we have talked. We have already talked. Now we have to talk of the system. So I'm telling you, I told you already that whenever you deal with the solar energy, in the very beginning you have to decide that what route you have to apply, is it thermal or the photovoltaic, because the system is entirely different. They will work on different working principle, and there is no similarity in the system. So that means a separate system will be required for solar photovoltaic. So where this we can convert this solar radiation directly into electricity. So we call this the solar photovoltaic system, or the device is known as the PV cell. And the other thing is the solar thermal. In the solar thermal, the solar collector is known the. I think whenever you talk about, sometimes we use even for PV also the solar collector. That should not be termed as the solar collector. The thermal energy system, solar thermal energy system, should be known as the solar collector, and this is not the solar photovoltaic or a PV cell. So that means that further the solar collectors can be classified the focusing type, flat plate, and under this flat plate again we have the depending upon the type of the fluid, the liquid heater or the air heater. I don't know. I should go fast, I think. So here, the roots of solar energy application is okay. Direct electricity, that's okay. Then next, solar collector. We will. I don't know how much I should clear this. Anyway, we'll see that. 5 minutes or here and there, no problem. So this solar, I just say that the solar collector. So that means a system. Now we call this about the system. System, when you need the solar energy, you want to use as for your application in terms of the thermal energy. So that means system is known as solar collector. So solar collector can be defined, I think, if you listen properly, it is the device which collect the intercepted solar radiations, and this convert that solar radiation into thermal energy, and simultaneously transport that heat energy to your load. So that is the complete definition of solar collector. It is there. That means solar radiations will be falling on the device, and it will be converted to heat energy, and that heat energy simultaneously should be transported to your demand, your load. If your demand is within the system, it's okay. If it is outside, then you have to transport that heat for the heat energy for application. So in that case, we further can classify into two categories, that is the flat plate and concentrating type. The flat plate can be known as the non-concentrating. So it's a simple device, just a solar water heater is a device that, okay, it's there. I think it's very familiar to you, and basically this concept of low temperature device, that is solar collector, mostly used for water heating, or the you can say this for this is low temperature, that's up to 100 degrees centigrade. Any applications you want to have that, basically hot water systems are being used for that. Here, let me slightly the concept, or because we are already, you want to develop the models and this so let us talk about little bit that how you can develop the model by knowing the concept about the solar air heaters or the solar collector, because we are using air is the fluid as a air, so that's why there is a solar. So what is the simple construction? Let me tell you that it is there. That means there is a box. In that box, we have a absorbing plate, and here is the glass. This is a transparent cover, and this hot plate, I can say absorbing plate. There are this some some fluid carrying passage will be there. It could be in the form of the tube, or it can be the integral part of this absorbing plate. So what happened? The solar radiation, that I can say the HT you have determined already. So it has to be transmitted through this glass. What is the, because ultimately that solar radiation should be absorbed here, so they should be absorbed over here. So if I don't put this glass cover, what will happen? That it will be absorbed, but simultaneously winds will be blowing over this, so that the wind may take that heat which is you have absorbed. So that will be that can be taken away from that. That will be losses. So in that case, we put a this glass cover, so that what is that glass cover or the transparent cover, so that the solar radiation can transmit through this, depending upon the transmittivity of this. So that means then they go to the absorbing plate and they get absorbed here. So in that case, they will get absorbed. So that means the solar radiations will be converted into heat. Then this temperature of this plate, or the thermal energy absorbed by this plate, has to be carried by some fluid, because that is the only transporting mechanism. So that means if the cold fluid in this passage, which is just attached with this, in contact with that, so that means that heat can be taken to your load. So that is the working principle of that. So here this part is the insulating part that is there, that is also insulating part here. So that is the flat plate solar collector. So in that case, if you want to develop the energy equation or the efficiency you want to know, so that means the rate of energy utilized, rate of energy received by the absorber plate, and rate of energy losses. That is the three things. So finally, that term, that the equation, I can derive that, but time is not there. It's not. It will not allow to me. So finally, it will be in this form. That means the thermal efficiency of a flat plate or a solar collector will be, it is like the FR tau alpha. This is written over here, you can see, but and this UL FR TI minus, sorry, here I can write. So finally, you can correlate that expression by, I tell you that the thermal efficiency of flat plate solar collector will be represented by a straight line whose this slope is negative and intercept. This is the thermal things, and this is T I minus TA by HT. This is the things, because you can see here, this is the this equation is straight line where this x-axis is this, and this FR tau alpha is the intercept. So that means here, or you can say here, that is the C minus plus minus M is FRUL, this, and into x is TIA by TE. So that means when you talk about the efficiency of the system, so it cannot be expressed in terms it cannot be expressed in this simply saying that this must be efficiency of the system. It will depend upon the under what conditions you are operating. Let me tell you that suppose you have the solar radiation this much, and that you want the temperature rise of this order. So that means you can determine the value and then go that value. So that means efficiency will be expressed accordingly. So that means it cannot be expressed in terms that my system efficiency, which you, because this line, this the thermal efficiency line is fixed for you, the system which you are using. So in that case, whenever you want to determine the efficiency of the system, you must have this graph from the supplier, so that you can find out the efficiency according to your requirement. So it varies. It can be 10%, it can be 80% or 70%, depending upon this value. So this is the things. Now I don't know. Let me go faster. Uh, this is a focusing type solar collector. It is for high temperature, and basically it is the modified solar collector. If you modify this with this, what is that? In that case, the solar we have a receiving surface, a receiver. We call this concentrator. So the solar radiation, of course, it is because the receiver has to be some curvature, and this curvature is to be designed based on the beam radiation only, because you know that at particular location, at particular time, what will be the angle of the incoming solar radiation, and that will be about the beam radiation only. So based on that you design this, and based on that you track this accordingly, just always facing to the sun. So that means by knowing the direction of the beam radiation, you will design. That is the basic concept to design the focusing type solar. And about the diffuse radiation, you don't know anything. So that means I don't consider that. So that what is there, that when you just when this beam radiation falling on the receiving surface, it will be reflected back on the receiver. So that receiver is of a smaller area than this. So that means you are concentrating. You are concentrating the energy. You can get the high temperature. So that is the basic modification in the flat plate collector, to have the focusing type solar collector in order to achieve the higher temperature. And how much, what is the order of the temperature, that will depend upon the combination of this concentrator and the receiver. So that means we have basically theoretically we have, if you have the plane reflector means the concentrator I'm talking about. That means it can be like this only, and then number of one more here, and then you can have the receiver here. So that means this is the plane reflector and plane receiver, both are plane. Then we can have the concentration ratio is about 1 to 4. A simple flat plate solar collector, we have the concentration ratio is 1. What is this CR? CR is nothing but the area of the concentrator or reflector, and area of receiver. So that means if in flat plate collector, what we have, the area of the interception or area of receiver is same. So that means the concentration ratio 1. So this is the things based on your requirement. You may select the type of the this you may select the combination of the concentrator and receiver. So here this conical reflector and cylindrical receiver. So all these things you can have. So the maximum temperature or the concentration ratio you can get this if you have the paraboloidal, that means the dish antenna like concentrator, and this receiver should be the spherical, not cylindrical, spherical. So in that case you can get this concentration up to 10,000. So that means high thousands degree centigrade you can get in this. So these are the basic things, and based on that we have different type of I think I just show here. This is the parabolic, this is a Fresnel type, and all these things I think we have the based on this concentration ratio depending upon requirement, and we have I think I just providing the notes for this, so you can read that, you can compare this, that which will be which have the disadvantage, advantage, and there is characteristics or the comparison of various solar collector. I don't read this because otherwise I'll miss other part. So I think you can you can I'll share this with you, then you can have this. So now Again, because if you talk about the um, a device, that means I told you that if you want to generate electricity from solar photovoltaic, so there is a direct conversion of electricity from solar energy, that is PV, but other route also, that means you can follow the thermal route also to generate electricity. So in that case, it is the route of just like the other thermal power plant. In thermal power plant, you use the different kind of fuel in order to generate the steam, and then steam will be go to the power block, and then power block will generate the electricity, and it will be distributed accordingly. So here also, that means you instead of the boilers and using the conventional fuel, we just heat the water and generate generate the steam by using the concentrating type solar collector. So that means the only thing up to this collection system, this collection system is the only system which you have to design. Otherwise, this power block will be the same as you have in conventional thermal power plant. And of course, this is also that because there also we can store the energy in the thermal plant, but there is no need to that. Means if you don't need power, you stop just burning the fuel, because that is in your hand. Of solar energy, you don't want to lose the incoming solar radiation. So in that case, it is recommended that the thermal energy storage should be integrated with this power between power block and the solar field. So that means here some technology very easy, convenient to integrate the solar thermal storage. So that's why there's another component important in the solar thermal energy storage. So this is also, we have different type of solar energy storage. Let me complete this. So that means I tell you that the classification of, we have different type of thermal energy storage, and this part at least I'm in hurry, but you can use you can take the advantage of these notes. And there's a lot of research area in this particular component of solar energy solar thermal energy system, that is the thermal energy storage. So in this, there are two types of the sensible heat storage and the latent heat, the phase change PCM. So the PCM and sensible, you understand that because in the sensible, the medium doesn't change its phase, it store the energy, that will be the liquid or it will be solid, in solid also. So there another, in solid there are the large particles packing elements, or the pack bed, sometimes it is not the solid one, and the liquid one, so mostly it's water we use. And so these are the advantages and the disadvantages. You can read that, and then the classification of the phase change material also there here. Because this is self-explanatory, you can read, and because time constraint is there. So here, drawbacks of the sensible, and now the research area I'm talking about. This I want to talk to you. That means the conventionally the sensible storage systems are there, latent heat storage systems are there. They have some drawback. So what we can do nowadays, the work is going on the combined sensible and latent heat storage system. That means you can develop a system by not integrating, by combining that two different storage material, like sensible as well the latent heat storage system. So that research is going on, that is there. That means in this you can mix these the packing elements, that is solid as a sensible, and for PCM you can keep in you can encapsulate that and then mix that. So in that case, some drawbacks, that means it is advantages sometimes. So research is going on that, so you can read that. So these are the various methods, and we can enhance the efficiency or the performance of the sensible store. This is the area we are working here in that case. So this is schematic, very simple. You can develop this experimental setup in your place also, because all these components are not that difficult to buy. And this is, I think, research papers are there. If you just search in the storage, the thermal solar storage, there's a lot of papers are there. You can. So I just have this 15, 20 minutes. So do you have any questions? Just 2, 3 minutes so that I can shift. Depending upon the time, I can discuss the photovoltaic system also. Hello, participants.
Sir. Yes, sir. Sir, I'm Puneet Bhatt from Mechanical Engineering Department, working as an assistant professor in Professor Rotary Institute of Chemical Technology, Ankleshwar. Sir, I want to ask that I'm currently enrolled in a PhD program and want to pursue my PhD in a solar energy thermal systems. So, can you guide me like which particular approach should I take, in which particular direction I should?
Solar thermal you want to do? Solar thermal or solar photovoltaic? Mechanical department, you have solar thermal you want to do?
Solar thermal. I want to pursue on a solar thermal, sir.
I think there are two aspects. There's the solar energy collection
Yeah.
device and the storage device. There are two different areas. So in the solar collector device, then you can have the performance enhancement of solar air heaters. A lot of work has been done in that area, but still there is a scope on that. And in that you can go for the single pass, double pass, artificial roughness. You can use the nanoparticles in that. So that means quickly I can say that you can go for the solar air heater in the this energy utilization system, solar thermal. As
Okay,
far as
sir.
the solar thermal storage, so there is still a lot of scope in that to work out, and I think it's an emerging area also in the government schemes. The solar it is storage, under storage, that you can say the solar thermal energy storage. And in the solar thermal energy storage, there are two things, that's a latent heat or the sensible storage. A lot of work has been done, and still there are a lot of scope in that. So I think you go through the literature review, you will find out the area. So I think immediately you want to the area, in which area you want to pursue in the solar thermal. So I'm
Yeah.
talking about these two areas are emerging area, that is the in collection. Even I'm telling you that people think that there's no practical application for low heat, this like the flat plate solar collector or that thing. I'm telling you that one day it will come. So the research which is going on nowadays, it will be useful after a few years, after some times, when, because still our focus, the government focus is not towards the solar thermal. Its focus is on the solar PV only. But when some schemes will come, so that means there's I think you can go for the solar air heaters. Different techniques are there in enhance to their performance. And second is the solar thermal energy storage. You can go for sensible, you can go for the latent heat PCM, or you can say combined also. And there's so many there things are there to do. Okay.
Okay. Okay. Thank you very much.
Right. So I think let me finish this. Otherwise, there's another important part here: the solar photovoltaic system. So here, that directly we can get the electricity, and there's a different. If you talk the solar photovoltaic system, so typically, what are the components of the solar photovoltaic system? Typically, I'm talking about. Otherwise, it will be need based. Suppose I need water pumping only, so that means I may not need all these things. Directly, I can connect this energy conversion. Energy conversion means that's photovoltaic cell or photovoltaic module, and there is a power conditioning is required. Power conditioning means because the conditions or the quality of energy or the electricity may not be directly useful for you. You need to modify this. You want to convert this from these, because PV generator generate DC, so you want to convert DC into AC, so you need conditioning of this power. So inverter will be, so that will come under the power conditioning unit. So that energy distribution for energy use, or it can be grid connected, or it can be sometimes when you talk about the photovoltaic system off grid, or so that means energy, or nowadays in grid connected also the people are recommending the energy storage. So the PV generator and the storage battery and power conditioning unit and grid auxiliary concern. As far as the PV system I'm talking about, So this, I can say that already the well-established technology for batteries are there. Of course, then emerging technology are there to enhance the battery for particular PV. So the work is going on the battery also, and power conditioning unit, maybe the inverter. There's so many electronics, so there's so many devices which need to condition the power. So the research is going in the power electronics also, and of course the interfacing. There's so many issues are there to interface this solar PV to the this grid. So that there's a research area in this research scope in this area also there. People are doing, but as far as the concept of the PV system, so the main component is the PV generator. So in the PV generator, I can say that sometimes there's a confusion, because I'm talking about the different, I'm talking about the concepts only, the basic things also. So sometimes we call this, we use the different terminology for PV generator. So basically, PV cell, the solar cell, they are manufactured in mass. They are produced in mass, and then these are connected in mostly in series, nowadays parallel also, but earlier they were connected in series to make the module. So that means in the market, this particular system, I think it is readily available in the market. That means this is the final product which is produced in a factory or in the industry. After that, so that means if the number of cells are connected in series to make a module, that particular generator, I call this a module. Then depending on your requirement, you can buy the number of modules and then connect them in parallel and series depending upon your requirement. So that will become a panel. So that means if number of panels are installed at one in one vicinity or at location, so that complete system of PV generator will be known as the array. Suppose I buy number of modules, I cannot buy the cell and assemble this. I can buy the number of modules and then assemble, make the panels. The combination of panel will depend upon the other power electronics or power conditioning units, as say the rating of the inverter. That this again, of course, is the things. But the terminology: PV cell, module, panel, or array, like this. So I don't know. I should speak this the fundamentals. What is the, anyway? So what is there? That means in PV cell, in the simplest way, that means sometimes it looks like a magic that how this solar radiation converted into electricity. So that means it is not alone the property of the solar radiation. It is not the property of the material. It is the combination, is the property of combined property of the solar radiation as well as the material. And further, you have to provide some provision within the material, then only you will get the useful power from the material or the PV cell. So what is that? That means you have semiconducting materials. What is the conditions to get the electricity? That means when solar cell, the solar radiation that in the form of the photons, they just fall on the active material of the cell. So that means they dislodge the electrons from their bond. So that means that energy is gained by that electrons, and it is dislodged from its bond, so that it now becomes free. It is free to move in this material, within this material. But until unless this charge particle, which is the energy carrying charge, you can say the energy carrying particle. So that means until it will come out from the material. So it will otherwise it will move within the material and it lose its energy, and that energy will be converted in the form of the heat only. But I want to take this electrical energy, this charge I want to take. So that means we create the PN junction within the material. I think it's again doping process. I think other we have to, there's no time to discuss, but that means it has to come out here, and then from here you have to take through the external circuit to your load or the battery. And after that, when this particular this transfer that extra charge or the energy to the battery or to the load, then you have to send it back to the material. So this is the process of this simple. And the efficiency of the cell can be simple. You can that the output of the cell and this how much solar energy intercepted, or the area of the cell, you can say. There are many ways to define the efficiency also, the effective efficiency. There's so many ways. That means depending upon that your requirement, that because if somebody is doing material some research on material and he want to know the efficiency of the cell, so his interest is to know that the effective area, surface area of the cell. He will not consider the area occupied by the frames or the grids, that things. So that is the things. There are so many ways to, it is available in the literature. So then now the problem is that I'll take this 5-10 minutes to a simple method to size the PV in that case. So what is there? The basically the output, or the like other electronic device, this output of a PV cell is represented by IV curve, and you know that's IV curve. Also, that means let me tell you here what happens. Suppose you go to the market, the concept I'm talking about, and you buy a module, and this module is specified by some rating, and if it is rated by this, suppose 120 watt. So not watt, you have to write this P, this is peak watt. So what is the meaning of this WP? So it is not the maximum wattage developed by that. It is not the average. It is the power generated by the system, what is the under the standard conditions, and those standard conditions are given, specified globally, that if the solar radiation intensity of solar radiation is 1000 watt per meter square and cell temperature is 25 degrees centigrade. I think there's another research is going on this, but I am talking about, that means you have to consider that. Otherwise what will happen? Because you know that if P is equal to I into, I'm not just using this ISC, VSC, I think these are fundamental things. I'm just explaining that how you can use that. So that means in that case, what happens if you buy this 120 watt peak watt module, and that is you don't have the 1000 watt per meter square solar radiation, how much it will deliver under the actual conditions of different solar radiation. So in that case, it is found that it is directly proportional. This current is directly proportionate to the solar radiation, and if you have the higher solar radiation, you will get the higher current. Accordingly, it's directly proportionate I'm talking about. That means if 120 watt modules you put under 5 watt per meter square, so it will give the 60 watt. So that is directly proportionate. How it is, this power is varied, considering this current is directly proportionate, and voltage, of course there is a slightly drop in the voltage, but that is negligible, so that we don't consider this. So that means the power is also directly proportionate to the solar radiation. So that way, otherwise say this area is ocean like, I cannot discuss so many things. And now the cell temperature. The cell temperature is also affect the output of the module. So what is that? How it? So that means it is concluded, or it is found that the current slightly increase, and which we consider is negligible, slightly increases as the temperature of cell increases from 25 degrees centigrade more. So that means if the cell temperature increases beyond 25 degrees centigrade, slightly increment in the current, but which we consider negligible, but there's substantial decrement in the voltage. So voltage will drop. So that means that effect we have to consider in the actual conditions. So, and here I'm not talking about it's directly proportionate. It is decided by a factor which is supplied by the voltage drop factor supplied by the manufacturer, and it is supplied, it is given by the, its value is determined during the testing of the PV cell. So in that case, how you can find out the voltage you can find out the initial voltage or rated voltage minus that factor is you have to multiply, and this dV, and the temperature rise, that means the cell temperature minus 25 degree. This is given by some millivolt or volt per degree centigrade. So that means any increment in the temperature, it is multiplied by this factor, and that will be reduced by that. So voltage will drop accordingly to that. So that is the factor we have to consider. Then Professor Pertham, Professor Pertham Arora.
Yes, sir.
Can I take five minutes more?
Sure. No issues in that.
Okay. If these participants are not getting bored, then I can take this liberty. Otherwise, I can say okay.
5 minutes only, one difference.
Okay, 5 minutes, in 5 minutes. So I think this is very important things I want to note. I tell you, there's a simple, the concept of sizing of PV, how you can size. So the sizing means, I just tell you if I have this fresh thing. Let me, notes are there, you can read, and I think you will get the things. But okay, let me, okay. Here only, okay. So that means sizing means I'm not going to design the module. I'm not going to manufacture the module. So sizing of PV means that means how many modules, because the standard modules are available in the market. You can choose those more modules of that standard, as I told you. And the sizing means your requirement. Say you have determined your, of course, this sizing method I'm talking of the off-grid system, where there's no need to put the power in the directly you are using for your application, for your house, for your village. So in that case, suppose you have some demand you have to estimate first. So what is your demand? And I tell you the most important thing is that for off-grid system, the PV system sizing is based on daily basis. So that means it is not the monthly or annual base, it's a daily base. That means how much energy you need in a day and how much energy will be supplied by the system. So for that, what you have to do, finally, based on the available solar radiation intensity or the energy, you have to find out the number of modules, so that will be able to supply the power to fulfill your need. So that is the things we have to consider. So sizing means number of solar modules you have to consider. So I think I just take this 5 minutes. I have to finish in 5 minutes only. Otherwise, yes. So see that this table, this is solar radiation at one location. So what I can do, I think for daily basis, I have to design the system. So this is the solar radiations. So here, these solar radiations, I can take the average. So that means these radiations are for 12 days, because one day for each month. So 12 days. So that means I can add this and divide it by 12. So I can get that this much solar radiations, average solar radiation available at that location. So suppose that comes, suppose 6 kilowatt hour per meter square. So that value I think I can take from this solar data, and then my requirement is, say, let me now come here. Wanted to connect it very nicely, but because of the time, no problem. So what we have to do, so to design, to size or to determine the number of modules, what I have to do, I need that how much, suppose I have 4,000 watt hour per day. This is my requirement. This is 4,000 watt hour per day, my requirement. And the solar radiations are available, say kilowatt hour per meter square. This is the solar radiation available. And I want to select a module whose rating, say, okay, 120 watt peak. These things I have to take. Now, how many numbers of these modules I should buy so that my requirement will be fulfilled. So in that case, the problem is that I don't estimate, it's not easy to estimate that how much this solar one modules will produce how much watt hours in a day, because 120 watt per is against 1000. So I think I can translate this, I can work out this, that in the peak hours means if I write this, I can write this 6 hours, I can write this term, and 1000 watt per meter square. This figure I can do like this. So in that case, that means this energy, if I take in the batch of 1000 watt per meter square, how many hours it will be available? 6 hours. So that means you can multiply this for 6 hours. So that means in one day, this module will be able, it's estimation. I think don't raise the question that will be there. There's so many things I have to work out. This is the research gaps, you can say. But I'm just estimating. I'm giving the thumb rule. That way you can do. So that means based on this, I can find out that in one day, how much watt hour my modules will produce. So that way you can divide that with that. So that means that will be the number of modules. And one more thing is there, that means you have to connect in series and parallel. So in that means to find out the number of modules or the string in parallel, you have to find out the voltage, nominal voltage of your load and voltage of one module. So number of modules will be maybe say 2 like this, and that means then current also, that means because you have to divide the voltage. So how much ampere hours you need in a day, and how much ampere hour you this your module will produce. So in that case, you can find out the series modules in series. So what you can do, that means it's okay, not series, in parallel. This is in parallel and this is in series. I think this is the impact of the going in hurriedly. So in that case, what you have to do, so that means you have to connect, suppose 10 modules in parallel. That means current will be fulfilled by 10 modules. So that you have to connect those 10 in parallel, 10 modules in parallel. Okay, in this. Okay, and then this two strings will be in series. So that way you can do that, and I think that's all. Thank you very much. Sorry that I could not go fast to cover the entire things, the concept. There's so many things I just skipped out. And so thank you very much from my side. And if some questions within the prescribed time you can have, then I'm here to answer. Otherwise.
Thanks a lot, Professor Saini, for such a wonderful lecture, like such comprehensively describing all the solar technologies, as well as like linking it to their simulation as well, which would be helpful in the later sessions. So maybe in the interest of time, I would request the people, if they have any questions, to put in the chat box, and I would request to answer them later on, because we have another session and I want like people to have a break as well. Will that be fine, sir? Like if they can put in the chat box?
Yeah, yes, sure, yes, sure. I'll respond.
So yeah. So in case anyone has any questions, like please feel free to put them in the chat box, and we'll deliver them to Professor R.P. Saini. So yeah, the next session again begins at 11:30, and it would be taken
Send
by, yeah.
Send a PPT on a mail. Send a PPT on mail.
Yeah, we will share all the PPTs. Don't worry about that. Maybe by end of the day, or by tomorrow. And the next session begins at 11:30 by Professor Ridham Singh on again the concepts of solar energy modeling. A small request to everyone that I have been seeing people, they are entering by some weird names, like some combination of like words and numbers, which doesn't make any sense to us. So in case you want us to take in your attendance, you should enter your proper names, because I don't believe you would have so much time to relate all the names to the weird combination of the numbers and the alphabets that you have put. Also, I'm also observing that certain participants ended joined in the last 10 minutes. So we wouldn't be able to add them to attendance if you are just attending the session for 10 minutes or so. So these were some instructions, and hope to meet you at 11:30 again. You can choose to remain in the session or log out. Like I leave that up to you. And let me check if there are any questions in the chat box. Okay.
Pratham sir.
Yeah.
Pratham sir.
Yes.
Yeah, this is Dr. Adhikari. Actually, I joined, then again I left, again I joined due to network issues. Means, so I
Yeah,
hope my attendance will be counted.
Yeah. We understand. We have like this is something that we don't have a control over, but there are certain people who joined in the last 10 minutes. So I'm just telling about them.
Okay.
So
Okay.
we would expect that people would be losing their connection, and like that is something no one has control over. And yeah, and also like I believe you would be compassionate amongst us, like on us as well, because like there would be some time gap before we allow you into the meeting, because we just can't allow everyone to join as soon as they put the join button. It takes some time. So I believe the participants keep that in mind.
Sir, I have a request, sir. Hello, sir.
Yes.
Sir, actually, my chat button is not active, so I couldn't write my name. So attendance will be I joined. That will be attendance, right, sir?
Yeah, but like the name that is written should be some proper name, should not be of some weird combination that I can't make a sense of.
No, sir. My name will be
So if
starting like Rahul Roy, sir. Rahul Roy 819.
Yeah, that should be good enough.
Okay, sir. Thank you, sir.
Yeah, like I'll just give you an example. Like I can see a member with the name ESR 192627.
Okay,
So
sir.
these are the types of name that we would not appreciate.
Okay, sir. I have a question, sir. You deliberately put a switch off the chat button, sir, or for me it is.
Professor Pratham, may I leave?
No. Yes,
Hello?
sir. There are no questions as such.
Okay, I can.
Thank you again, sir. Thanks a lot. So yeah, we are not deliberately putting off the chat for anyone. That is something we can't control at all. You all have the privilege to have the chat. But if you're not getting that option, that is a bug in the Teams app. So what I would advise is try using the browser or in different browsers or using the app. Which one works for you?
Okay, sir. Okay.
So